Hi. Now that we're got a schedule, if you will, using CPM, what we want to do is to kind of take a step back a little bit and look at, first off, the activity times and how we calculated them. Clearly, they are an estimate. And as we saw with cost estimates, there's a deal of uncertainty associated with them. Now, in cost estimating, we were able to use PERT to enhance not just our estimate of what the cost was going to be, but also a better understanding of the probabilities or the uncertainty associated with each of those estimates. And we're going to use that same technique when it comes to looking at the estimates of time needed for each of our activities. So it is true that in CPM, it assumes that we have a fixed time for each activity, but it actually integrates really nicely with PERT that the output of PERT can be the fixed time that we input into the CPM. Now the CPM won't update itself for that probability, but it will use the best estimate that the PERT will deliver. So let's look at PERT for a second and see how we're going to go about doing that for activity times. So similar to budget estimates, where we used three cost estimates, we're going to use three time estimates for each of the work packages or activities. We're going to have an optimistic, a pessimistic, and a most likely, shown here as A, M, and B. So the one thing we do know from the research and everything else is that the time estimates or the time probabilities are well represented by a beta probability distribution, and so that we're going to use the PERT using a beta probability distribution. And so the same formula applies that we used in cost estimating. So in this case, it's a T, or time, is equal to our optimistic time plus 4 times the most likely time plus the most pessimistic time, all divided by 6. And what this does is it weights your most likely time considerably, but at the same time gives consideration to your most optimistic and most pessimistic. Now, the other thing it does is it allows us to calculate the variance, and so this is going to allow us to use mathematical processes as far as probabilities and likelihoods of various outcomes. And so we have the equation for the variance. So variance is sigma squared is equal to, and it uses our two extreme perspectives, are most pessimistic and most optimistic. The difference between those divided by 6, all squared. Now, the one thing, we didn't really talk about this when we were talking about cost, but it's probably worth appreciating, is that this formula is set up when it assumes an estimate for your most optimistic and most pessimistic to be with that at the 99% confidence, and that may or may not be true. And to be fair, sometimes the mathematics can get away on us, and where we're applying judgment, and then the math forces us into a refinement which we're just not working at. But for clarity's sake, if you were comfortable that your estimates of most optimistic and most pessimistic were better represented either by the 90 or the 95% confidence, then you could just adjust the equation for the variance down to having a different number in the denominator. So instead of 6, it would either be 3.29 for 95% confidence or 2.56 for the 90% confidence. And this would just make your probability calculations that we're going to look at that follow in line with the confidence of your estimating process. So just keep that in mind. So what we need to do is we go back to our table. So we're going to keep working the same example in Milwaukee Hospital. And we have, in this case, instead of just a single estimate for our duration, we now have our optimistic, most likely, most pessimistic, and then we throw in another column in our spreadsheet to get the expected time, T, using the formula. So a plus 4m plus b all divided by 6. And now in weeks, we get the expected duration of all of our activities having used the PERT calculation. And while we're at it, we're going to go ahead and calculate the variance. Again, b minus a divided by 6 all squared. And that gives us our variance for each of our activities. And so we see the calculations going on for our activity times, calculations going on for our variance. We just drag that down through our spreadsheet. And of course, when we add up all of our expected times, this would be the expected time for our critical path of 15 weeks. So now, what really is great about this, so having applied PERT, we hopefully have got a better estimate of each of our activity times, and that's valuable in and of itself. But it also gives us a mathematical construct which allows us to look at the probability of the project completion times as a whole. So project variance is computed by summing the variance of all of our critical activities. Remember, we've already calculated now the variance for each of our activities. So what we want to do is to look at the variance of each of our activities on the critical path and add that up. And when we do that, we actually get the variance for the project. And so in the example that we're looking at, so we see the variance is equal to the sum of all the variances on the critical path. So I've taken these from the table on the previous slide, and I've put them in here, and I see that our variance for this particular project is 3.11 weeks. Week squared variance. And of course, the standard deviation is the square root of the variance, and so we can take this the square root of that, and we see that we have a standard deviation of 1.76 weeks. So this is where the real fun comes into it, is we actually now can figure out what a probability is of completing our project by a given time. And so if we wanted to look as an example of the probability that the project would be done prior to 16 weeks, remember 15 weeks is the time on a critical path, so that's the earliest it's going to be finished if everything goes as per our calculated time. And so we want to figure out what the probability is that it will be done at the 16-week timeline. And so the way we do that is we use this formula. We calculate Z, and Z is equal to, and so X is our target time frame, and nu is our expected time. So that's sum of all of our time estimates on the critical path. And we divide that through by the project standard deviation. And so we have due date minus expected completion date divided by our project standard deviation. So we have 16 minus 15 weeks, all divided by 1.76. And we get 0.57 standard deviations is the value for Z. So what does that do for us? Well, we're able to actually now either go to a table for a normal distribution and look up the value of Z and figure out what the probability is that we're going to be finished by then. And so for Z equals 0.57 standard deviations, we get a probability of 71.57%. So it is 71.57% likely that we would be completed this project by 16 weeks. So let's just look at an example of that to I guess help solidify it or send it home. So in this case, we have a project for submerged dynamics, and they build submarines. And the submarine retrofit project that they're looking at has an expected completion time of 40 weeks. It's a fairly simple retrofit with a critical path variance of 25 weeks, which is fairly large compared to the 40-week time completion. And then the question then is, what is the probability of finishing the sub retrofit in 50 weeks or less? And so we start with our probability, and of course we're looking for the value Z. And so we need to calculate that. So we take out our formula and we put in our target of 50 weeks less the 40-week expected completion time, and we divide that through by the standard deviation of the project. And so it had a critical path variance of 25, so the standard deviation is the square root of 25, and we get a z value of 2 standard deviations. So what we need to do is to check the probability from the normal distribution table. So I show an image here of a normal distribution table. We could zoom right in and we could see that looking up z in this column of 2.0, we get a value of 97.725%, which is to say that it is 97.725% likely that we will be finished this project by the 50-week mark. Now, I show it using a distribution table, which is always helpful to get our head around it, but certainly all of these formulas and distribution tables and all that are built into formulas in Excel. So we can certainly draw the number out in Excel as well. So we've been looking at the completion of the critical path, but we've also talked previously about bias and how convergence can cause all sorts of problems. And so what we need to also do is to look at what the probability of completing by a certain time of our non-critical paths are, because they may actually impact us. So here is our critical path that we showed, but we need to find the other potential paths through the project and look at the probabilities of completion times for them. And so we will do it using the same formula and the same process. We need to add up the variances of all of the tasks on those paths, and then we're able to plug those numbers in and figure out what the probability is of completing those by the same amount of time. So if we were to look into our spreadsheet, we identify our 4 paths. So the first path is our critical path, which we already did. And we know it was 71% likely of being finished by 16 weeks. Remember, 15 weeks was our project time. And so now we plug in, so for the path ACFH, which is the magenta line, we know what the path time is, we know what the path variance is, we get the standard deviation, we plug it into our formula, and as I said, the probabilities are all built into the spreadsheet, so we can build it right into the spreadsheet. And it says it is, plus or minus 100% likely that it'll be finished on that time. Remember, there was a lot of slack in activity F. When we look at BDGH, so that would be the green path through, again, we do everything up and we get a 90% likelihood that it will be finished by the 16 weeks. And 97% likelihood that the blue path would be done by the 16 weeks. And so really what we can see here in this instance is that while each alternative path has a chance to delay the target completion, they're all pretty small compared to the probabilities of the critical path itself in this case. But you need to do that analysis to arrive at that conclusion. So let's look at another example using the same series of paths through our project, and basically ask a different question. What are the chances that any of the 3 non-critical paths will cause the project to be delayed from the critical time? So the critical time is that project time of 15 weeks. So before we asked, well, what's the likelihood it's going to be done in 16 weeks? And then what's the likelihood of the alternate paths interfering with that? And we got a set of numbers. But in this case, we're actually going to just recalculate the probabilities of each path being completed by 15 weeks instead of 16. And so we use our same table, only in this case we put in 15 as our target time, so that x value in our equation, and recalculate our probabilities. And in this case we see that some of our probabilities are getting down. And so path BDGH is most likely to cause a delay to the critical path, which it's 74% likely to be completed before the critical time. But it's still considerably less likely to cause a delay than the critical path itself. So merge bias. So we've been talking about merge bias before, but now what we want to do is to have a better look at the numbers. And so I've built up this construct before, and we were looking at what is the probability of milestone B being delayed. Now, I've changed the numbers from the PERT calculations a little bit going in so that they're not all exactly the same. The last time we looked at this, they were all the same. So what we know is that any time two or more paths merge, the probabilities of all the paths being on time is the product of the probabilities of the individual paths. So we've got a process and a method now of looking at any individual path, but what we need to do is to use this information to look at the probability of the merged paths all coming together. And so looking at our three paths, activity A, activity B, and activity C, we can, and we have it done up with our optimistic, most likely, pessimistic. We come up with our expected value, and we have our variance. So those are path variances because each of these activities represents a path for our project. And so this is the calculation that gets us to probability in the bottom half. And so for our critical path, which is activity A, so our target time is 13, which is the activity time for activity A, and that's what makes it the critical path. And of course, because it's a single activity, it has a 50% chance of being finished ahead of schedule or later. But then when we look at activity B and C, they're both 12 weeks. And so when we do the calculations on those paths, we see that they are 93% likely to be done by 13 weeks, which is fairly good. But if we want to know what the actual probability of milestone B being completed on time, it would be the product of 50% or 0.5 multiplied by the 93% or 0.93 multiplied by the 0.93 for activity C. And that gives us a probability that it'll be completed on time of 44%. Or if we look at the inverse of that, the likelihood that milestone B will be delayed is actually 56% and not 50%, which it was without the bias of the merging activities. And we've already talked about Monte Carlo simulation. The example that we used when we introduced the idea was one of time. And coming up with this distribution for the project as a whole. And this allows, or this tool allows us to look at much more complicated projects than the rather simple network diagram that we have sitting in front of us. So time reserves. So we already know, based on PERT, that in every activity has a 50% likelihood that it will go late and a 50% likelihood that it'll finish early. And that's the two sides of the probability distribution, either side of the expected time. And so based on that, even though some might cancel out others, we can reasonably expect that for our project schedule to work at all, we have to have some kind of a time reserve, that we can't just rely on chance that our project is going to stay on time, particularly where they are lined up and we're going to schedule resources and everything else based on the predecessor activities being finished on time. And so we're going to have to manage that uncertainty by having a time reserve. Now, time reserve can be managed in a whole bunch of different ways. It can be assigned to simple activities. It can be assigned to sub-projects. It can be assigned to projects. It can be done as percentages of estimated durations. It can be done as fixed time, or we can use our Monte Carlo simulations to try to come up with a more reasonable risk assessment that would give us a better value based on our risk tolerance and whatnot. But it is absolutely critical that we have some kind of a time reserve if we're going to hit our targets. It's absolute fiction, given the stochastic nature of the activity estimates or the time estimates, that we can hit them all. If we don't have a time reserve to fudge back and forth, because we're going to have a lot of our tasks are not going to hit that target. Arguably, by the probabilities, 50% of them won't. So before starting to close out, I did want to point out that what I've demonstrated in fairly simplistic graphics on the scene These are just representations of what we use in the more commercial softwares. So the diagram on the screen, that's just a screenshot of one of the sample projects that we've been looking at, done up in Microsoft Project. And to be fair, I even have it set up using the normal defaults that I use when I'm looking at a Gantt chart in Microsoft Project, where I have my critical path showing up in red, I have my non-critical activity showing up in blue. You can actually see the slack in the non-critical activities with the sort of dark gray lines coming off the end, and that represents the slack that each of those activity has. And of course, the precedents are shown with the arrows. So the tools are great. They all have their idiosyncrasies. I certainly have a series of tutorials that I run for the undergrads in Microsoft Project, and I don't have them done yet for the current environment, but I am committed to creating those online in the coming months. So we'll be adding that as just a resource that would be available. So I hope that the advantages for PERT and critical path method, for that matter, are obvious, how they will help your project. Now, to be fair, depending on your industry, or if you're going down a methodology like Agile or something like that, most of this will not be used, but I would say the vast majority of projects are still using a fairly deliberate scheduling methodology. And yeah, when you get into a large, complex project, it is so difficult to manage small, the complexity of the activities and the scheduling associated with those activities without some kind of a tool. And of course, the tool that I've resorted to is the Gantt chart, but it's the Gantt chart that has been empowered both by PERT and by CPM. So the CPM process and the PERT process, quite frankly, they are fairly straightforward concepts. They are not mathematically complex. Once you do it once, twice, program it into your spreadsheet, you're not really going to forget it too easily. And the graphical networks are so valuable when it comes to not just scheduling your project, but then controlling it and reporting variance later on. So the critical path and slack time analysis, they certainly help inform you of the flexibility that you have in order to try to make everything else work. Remember, we still haven't talked resource scheduling. And with that, as we talked about in budgeting, of course, we're assigning our costs by activity, and so we can report not only on time variances as we're going through, but we can also report on cost variances using these tools. Now, everything that has an advantage, of course, comes with some kind of a limitation. There are limitations to both PERT and CPM. The assumption is, when we did this, is that these activities are defined, independent, and hopefully stable in their relationships between each other. Otherwise, that network diagram is going to lose its logic connection and kind of fall apart. Now, we also have to identify those precedence relationships, and as I alluded to as we were going through, sometimes your own scheduling bias can start to impose constraints on that aren't actual real physical constraints. And but I think as you grow experience and you learn your own idiosyncrasies, you'll be able to deal with that. Of course, time estimates are subjective, although it has been demonstrated that the PERT method can enhance your time estimates, and certainly going through that process, the thinking process of coming up with the optimistic, pessimistic, and most likely is of value even in refining the most likely. Now, do managers fudge timings? Sure, everybody fudges timings. We'll talk a lot more about some of those human interactions and limitations as we move on. So yeah, it is worth pointing out. I mean, I certainly emphasize, the value of protecting the critical path and protecting the critical path, but you can't protect the critical path excessively at the expense of your other paths, because as we see, it is the confluence of the probabilities which is going to matter. And if you protect the critical path without paying due diligence or due attention to the other paths, then you risk it no longer being the critical path, and all of your resources are lined up to protect the wrong path going through. So don't lose sight of the entire network, but use the information for what it's worth. And yeah, it doesn't incorporate resource constraints or leveling. And so that's kind of the next step. We're going to have to look and see how we can use these tools to now schedule our overly constrained resources or otherwise level out the resources that we need. So that will be our next step, is to look at resourcing and resource scheduling.